Good afternoon. Welcome to the course Thermodynamics of Materials. Uh, this is actually the lecture 67 and 68. Dynamics. We have thermodynamics of materials. So lecture 67 and 68, we were discussing Ellingham diagram, which is actually delta G0 versus T plot for actually number of oxides, and we study relative stability of oxide with the help of the Ellingham diagram. So I will not actually repeat what I said last day, but to continue I have to just prelude something. Okay, that is, we are considering two oxides to study the relative stability. Two oxide, one is AO2, another is BO, and as Ellingham diagram requires 1 mole of oxygen, you must consider this is the basis. So with 1 mole of oxygen, there is some rationale behind this, though. Okay, we will understand later. That is A plus. Okay, these two lines I have already given you, and these are the delta G0. Remember, the plot is delta G0 versus T, and we got this. See, so we are actually studying the relative stability at temperature T1. First of all, consider. I consider three temperatures: T1, T2, and there is where the two lines intersect, T. So we found actually got the answers. The question was this. Question was said, we have taken in a closed system in a constant volume. This is a constant volume reactor, isothermal as well. And we took this AAO2 and BBO, the four species and the gas in a constant volume reactor. It is the initial state. This is the initial state, this I discussed. Then question was, what is the equilibrium state? Means which oxide will be present in the equilibrium state, or which metal will be present. And this actually, what is the pressure, final pressure? These are the questions. So we actually studied this. We found that under these conditions, the condition is what? This temperature T1, you please note that this is the AO2 line. It has actually delta G0 is minus 60, while BBO line, this line, remember, the intersection means this is above this at the temperature below T and below at a temperature above T. So intersects and they actually swipe their relative position. So of this. So what is this? This is minus 60, minus 40 at temperature T1. Based on this, we discussed. And we found this, that this reaction, we actually started from the scratch, and we found that AO2 and B will be stable. No doubt. And this is actually justified by the delta G also. What is it? If we consider this reaction without considering this, okay, step by step, etc., piece by piece, we found that this is delta G0 is negative. And delta G, since delta G is the criterion always, delta G happens to be delta G0 because these are all standard state, pure state. So delta G is negative. Hence, this negative, why? This is like, if we consider this, just this is algebraic. Minus 60 minus 40, minus 60 minus 20. So we all said, so this reaction is spontaneous. So no doubt this reaction will produce these two. So these two are stable. Question whether what will happen? Will both of them disappear, or one of them? And one of them, who it will be? Which will be actually left behind? Like this question. And what is this? And the gas. What is the pressure? A very important question. What is the PO2? So this I say with this asking mark, okay, asking sign, this what is the equilibrium state, the temperature being T1 isothermal. So just quickly, we found the answer is this. See, his answer is this: AO2B must if A is A may be present as well. Why? Under what condition? When A is, consider this reaction, when A is stoichiometrically greater than BO, means it is more than 1:2. A is to B is greater than 1:2, like namely 2:2, 3:2. Then this B will be removed from the system. AO2 and B will be present. So this I have written. AO2 we must, and A. If A is excess, if this excess, then what is the pressure? Pressure, this you have to understand that AO2 will actually will exert the equilibrium pressure, which is this, what I gave you here, AO2 at the temperature 10 to the minus 12 atmosphere. So this is the partial pressure of oxygen. So the total pressure as well. The question is how you define an equilibrium state? By temperature, by pressure and composition. And now, and composition means mole fraction, etc. So what is the pressure? Now since it is only oxygen gas present, so this is the total pressure as well. The total pressure, temperature is already given T1, pressure and composition, these are all pure, sir. So these are composition means pure means mole fraction 1 and gas is single also. So its actual partial pressure and total pressure is given means this is actually same. So mole fraction 1, or say you just mention the total pressure and pressure that will give the composition of the gas phase, which is pure oxygen. So discussed. Now opposite. No, A is not excess. BO is in excess. How much it is? A is to BO is more than BO in excess. So what will be 1:3? I'm sorry, right? A is to BO will be 1:3, 1:4. Such. I'm giving perhaps somewhere. A is to 3:1. BO is to 3:1. So in that case, BO will be there. So what are the possibilities? What phases will be not possibilities? Which phases will be present? Again, you write this AO2 and B must, then BO. And what is the PO2? You have to see both B and BO are present, so they will strike their equilibrium pressure, which is 10⁻⁻10. This is the answer. This I discussed at length actually. That's you see here why B has no trouble with this value. B has no complaint. This I discussed. So today I'm not going to discuss. Similarly, I discussed that with this BBO equilibrium, AO2 has no grumble. AO2 has no difficulty to stay in equilibrium with this. So this, in all respect, this is actually complete solution. No problem. For example, I repeat this AO2. Say AO2 will be stable. Question. So BBO equilibriums are very good. Fine. BBO2, this oxygen pressure will maintain the equilibrium. But what happens to AO2? Let us see what AO2 can do. AO2 can get back to air and oxygen, dissociate back. So, but this will happen when? What is the equilibrium value of AO2? Tell me, 10⁻12. When AO2 will return to here, AO2 will return to A when the pressure is less than 10⁻12. Then it will dissociate back. When it is more than, try this way. Say if you are smart in forward direction, do that. Then you reverse then. Then you have to be very easy to follow. If it is greater than 10⁻12, it will follow. If it is then it is less than 10⁻12, AO2 will be dissociated back. So is the pressure less than 10⁻12? No, 10⁻12 itself. So no problem with this. Okay. If it were 10⁻13, -14, etc., AO2 will be difficulty, but no difficulty. Okay, AO2 will remain there with this value, etc. Oh, what is the pressure? I said I consider this case. Okay, anyway, in either case you will see. Here actually a problem with this. I repeat this. Taking time though. AO2 no problem. First case, AO2 no problem. What is the equilibrium? 10⁻12, and that is there. Problem with B. You may ask, sir, will not be oxidized? Will not be oxidized? Let us see. This actually you try to analyze this. B will oxidize. What is the requirement for B to oxidize? Any value greater than, this is the BBO line, remember, low, this one. So any value greater than 10⁻12. But what is present? I'm sorry, BBO line, what is this? Oh, any value greater than 10⁻10. But what is the value? 10⁻12. So no, so it remains in equilibrium state. So fine. So and I actually added then, I brought in phase rule to actually understand more about this, get more insight and more actually complete knowledge of this. When phase rule says if is, I explain this too, then I will consider the third case. Perhaps I started, then it was actually run out. We actually ran out of time. Third case. This actually I started when that exactly stoichiometry. Obviously, this question will come more than, less than, exactly, sir. Now, what are the phases? This is most important. Okay, what is this? I am giving the answer. This when exactly stoichiometry means both will disappear together. Then what is remaining? Sir, they have to and B. Why they are disappearing? Because they are reacting and forming them. So have to be and no other solid phase. What is the gas pressure, sir? Here actually interestingly I showed you physically as if. So this system is actually, I see this is once A2, A2, then BO2B, A2, A2, BO2B. This is happening, then pressure in the system is moving, dancing between these 2 points. Moving. And see any moment say it is somewhere in between, then their simultaneously disappears. You don't know which time, any time, but this will be confined between these two limits. So it can be this, can be this, can be any value between this zone. You know. So what is this? Now this time not unique, not unique, unlike before, that it can be any value less than equal to, less than equal to this range. This should be supported by the Gibbs phase rule. Then we'll be very happy. This I started actually saying this. Consider these two cases. First of all, you make a phase rule analysis for this one to first case. First case will actually, if you understand first case, second case same thing. How many phases? 1, 2, 3 solid and gas phase. So 4 phases. Phase rule Gibbs phase rule, which I may, time permitting, I may discuss, or I'll be sorry. Okay, time not available. F is C minus P plus 2. C is what? Number of components is nothing but go by the elements, I should say. So A, B, and O. Let's say nickel, copper. Okay, nickel, copper, oxygen. Nickel oxide or copper oxide, two oxides, competing oxides. So 3, namely A, B, O. Go by actual element. This is easiest way to get the components. And then what are phase? Number of phases is what? Tell me, there are 3 phases. Here, consider 1 and 2. These two. So consider 1. Explain the second. 3 phases and 1 gas phase. So 4 phases. I have written also somewhere 3 solid and 1 gas, which is namely oxygen. So you apply this 3 minus 4 plus 2 gives you a value of 1. Means you have a choice of one thing. And which you have chosen here? See, you written, who wrote this? You wrote. It can be not only T1, it can be another, any other temperature in the neighborhood. So T1, this side, these, like this. So this is a choice actually, means freedom you have used. So the one freedom that you have at your disposal, you have already used this in the form of T is T1, that is you have chosen. It is your choice. It can be 500, it can be 600, etc., etc. So these are actually one choice. So no more left. Means now system will automatically, all other things will be, you have no left. Means automatically fixed. By fixing this, you see, fine, yes sir, one side this, what are the fixed? You have the pressure, you have no choice. Why? Once it is T is T1, you know what is the PO2? PO2 will be 10 to the minus, first case, AO2 means 10 to the minus 12. You have no choice, no one can stop this. Why this 10 to, by the way, how do you get this value 10 to the minus 12? You remember this, what I said? Start from delta G0. Delta, I have written also today once more. Suppose this, A plus A2 is delta G0 is minus RT ln K. RT ln K, RT means T is T1, ln K, etc., etc. You get AO2 means PO2. PO2 will be just mathematically minus 60 subject 10 to the minus 12. So just if minus 60 is given, it will be, and temperature you know, then 10 to the minus 12, for example. Okay, so all are fixed. So it is very satisfying that phase rule also says one thing you fix, all other fixed, PO2 fixed. And in the second case, I will not show you because it is also similar case. Three three solids and 1 gas phase. So again, 1 degree of freedom. Temperature is again temperature T1, and this, since it is BBO, so the PO2 will be dictated by the 10 to the minus BBO2 equilibrium. Third case very interesting. There actually it requires actually little bit analysis, but very interesting. Third case, I am writing this here. Case 3 phase rule. Case 3 today. Case 3 application of phase rule. Application of Gibbs phase rule, of the phase rule. You may like this. Application of phase rule. What is this case 3? How many phases present? Take a look. You have understood which are present. You have already said. Tell me. A to B means 2 solids. So let me write first of all. C is what? C cannot change. A, B, O. 3 component cannot change. What is the number of phases? 2 solids here this time. 3. Good. 3 phases. P is 3. 2 solids plus 1 gas. Just right. 1 gas. So what is the F? C minus P plus 2. C being 3 minus 3 plus 2 is 2. Degree of freedom is 2. What does it mean? How do you interpret this? Degree of freedom, you say, sir, I have a choice of temperature, which is actually, what is the temperature? What you have considered? Sir, T1, my choice. And what is this? This time you have a choice. It is not unique. Not unique means you have choice. There is no compulsion. It can be any value between this range. So pressure PO2, P is total pressure is as good as PO2 is actually you can choose actually. What you may choose? Can you tell me which you may choose? Please tell me. Any value. You can consider this also included equals to included this. So better you take care in the range 10 to the minus 11, 11. Very good. See, very interesting. You consider Asa, this is my choice. You can check this actually. You can check this. This is actually equilibrium state. A2 one by one will you check quickly. 10 to the minus 11 atmosphere. So you see you have understood. So this is the application of the degree of freedom. Okay, 10 to the minus 11 imagine other things, but this is a freedom. Two freedom utilized. One thing you have checked this. Suppose 10 to the minus 11 you have considered. Now justify whether AO2 have no difficulty to stay in equilibrium under this condition. Question? Any question, sir?
Two solid phase and one gas phase.
And the third case. Agent, case 3, two solid agent. They are stoichiometrically present. In exact stoichiometry, in underline, in exact stoichiometry, so they go simultaneously, disappear from the system. No way. So now you verify one thing here. Suppose you have considered pressure of 10 to the minus 11 atmosphere, just for example, and very good example. With this pressure, do you have any difficulty with AO2 and B? You check. If AO2 has any difficulty with this pressure, means no, under this pressure AO2 will dissociate back into A. Then you will say there is something error, something wrong. Or B, first of all say B and 10 to the minus 11 atmosphere oxygen. B and 10 to the minus 11 atmosphere oxygen. Will it oxidize to BO2? No. So what is the requirement? No, minus anything greater than that. Where you will get this 10 to minus 11? So B is okay, but I am happy, satisfied. AO2 will, what can AO2 do? It can dissociate back only because it is in the oxide form, can back into metal form. So AO2 will dissociate back when under the pressure of 10 to the minus less than 10 to the minus 12. But this is 10 to the minus 11. So no sir, everything is fantastic. So this is actually our analysis. But next I'll remove this today. Actually, I'll tell you. You just mark this. That I mean this I'll pick up. This is the stable phase. Next line. Let us see. Okay. With this later I will remove this. So this is the rule then. Kind of axiom. What is axiom? So lower oxide. Take a look here. So this temperature, which is a lower oxide? Lower oxide or lower oxide? Which one? AO2 or BO? AO2. AO2 is stable, not BO. And B is in the metal phase. B is stable. Is it upper or lower? Upper metal, lower oxide stable. This is the gospel truth. If you in the Ellingham diagram, which is drawn on the basis of 1 mole of oxygen, don't deviate, then this will be actually disrupted. So can I write this? So we find that the lower oxide here, lower oxide at temperature T1 I am talking, lower oxide at temperature T1, okay, lower oxide, the lower oxide, which is namely AO2 at temperature T1, writing, and lower oxide is AO2. Why I am writing temperature T1, you can think. and lower upper and the upper metal B are the stable phases. That means actually the lower oxide is AO2, upper metal B. Okay, these are stable phase. That is AO2, I'm very sorry, AO2 is stabler than, write this, AO2 is stabler than, that is at temperature T1, that is at, at temperature, write this here, at temperature T1, mark this, why T1 you will understand, because if it is T2, you know, it will be reverse, okay, this will be a lower, that will be upper, so that will be, this is actually the flip-flop, okay, so AO2 at, so that's why temperature T1, but the rule same, at temperature T1 AO2 is stabler than, right, the oxide, right, the oxide, the oxide at temperature T1, the oxide AO2 is stabler than the oxide BO. This is your understanding. And, right, the metal B is at temperature the oxide A, and the metal B is stabler than the metal A. So here, so lower oxide, right, that is for continue. That is number of ways you say the same thing. That is a lower oxide, lower metal, lower, that is a lower metal can reduce an upper metal oxide, upper metal oxide. Can reduce forming, but the reduce forming I should not write. What it means forming key, what you can know, what is this? Forming lower metal oxide and upper metal. It's the opposite. I don't write this, but the converse is not true. But the converse is not true. This is okay. Very good. Converse is not true. So this is you have seen. Okay. So another thermodynamical also. Suppose if you say here at this temperature, this was continuous. This was continuous. If you wanted the opposite, get AO2 reduced by B, that means reverse direction. What is the delta G0 will be? Will be positive. Means that is not possible. So you see very clearly it is formed. Actually, basic requirement is delta G and delta G, actually delta G, and which is here in this case delta G. Okay, over this part is okay. What else I should say here? Achha. Now that is in still other words. Achha, lower again lower, the lower metal oxide system, metal oxide system has a lower oxygen potential. Which is this, sir? PO2 equilibrium. Key, what is this, sir? PO2 equilibrium, nothing else. Equilibrium oxygen pressure. Then a and then an upper, again a lower metal oxide system. That why not D here, right? A lower metal than an upper metal oxide system. PO2 is equilibrium. So you see, check which is here lower, which is AO2 is the lower temperature T1. What is the oxygen potential? It 10 to minus 12. It is a lower means smaller. I have written lower. It is better. English is smaller. Not lower. Lower is the position, and value is smaller value. So oxygen potential is very important. So this is actually governed by oxygen potential. This is the whole thing actually. So that's why for reference we have considered 1 mole of oxygen in either case for the purpose of comparison. So this part is okay. Over you can consider. So if you actually have, can I remove this? Remove this. Unnecessary. Let us move on. Now consider Acha. Next, consider these three lines. Next, consider the following three lines. Following three lines, three metal oxide system. Three lines, that is involving three lines for metal oxides. Three lines involving metal oxides. Involving three metal, involving three different metal oxide. Always you say metal oxide. AaO2, BeBO. This is actually how metal oxide system. I'm drawing these three here, sketching this. Delta G0, as you know, temperature. And some, you should mark somewhere zero is actually not zero is there. Okay, this is, remember, this is more negative actually. This is increasing means this is negative. This side is negative. This is zero, the positive. This is positive side. This is negative side, zero. And then I'm drawing three lines quickly. One. Oh, sorry, sir. Oh, it is not bad. This is bad. One, two, three. Yes. This line, alumina. This is, for example, Cr2O3. This is, for example, Fe2O3. Okay. This is, so if I ask you, so can alumina question? So question is it possible to reduce? Is it possible to reduce Fe2O3 by aluminum? Solid by aluminum solid? Aluminum chips? Yes, because this lower means oxide is stable. That means this aluminum can reduce, and that it's can reduce Fe2O3 to Fe. The metal, upper metal is stable, producing a stable phase. So yes, answer is, so right, Al plus Fe2O3 2Al, Al2O3 plus 2 Fe. Okay, this is actually used in where? It is spontaneous. Thermit welding. This is thermit welding used in rail, joining of rails. Thermic welding used in thermic welding. Achha, next is similarly I should say similarly Al plus chromium oxide producing Al2O3 plus 2Cr 2Al. This is also spontaneous. Okay, happy? This, now you understand everything now. This is possible though. Today you know that it is possible. But one day you use this without doubting. When? Thermochemistry. Thermochemistry, delta H cannot give the criterion of a reaction. Delta G can. So there, but you consider this. Remember thermochemistry problem? Aluminum 1 kg, etc. How many? But you consider that this reaction as if she is given. But you may ask, are you sure of this reaction will occur? This question can be asked only after the second law of thermodynamics started. So since we have, through this we have completed, so we can ask, yeah, yes sir, this can be, this is possible, and you can set up a problem using this aluminum and chromium oxide. This is all. So the smart writing. So these are known as, see, one metal is used for reduction called metal. These are examples of, this is a category, are examples of metallothermic reductions. These are called metallothermic. This term metallothermic reduction. Metallothermic spelling is correct. Huh? Metallothermic reduction. So example is, we get e.g. aluminothermic aluminothermic reduction. You may have to use this in your project, undergraduate or say later PG. Okay, aluminothermic reduction, aluminothermic or calciothermic. You understand what is calciothermic? With the help of calcium is the lowest one. It can reduce everyone as if calcium. If we follow last class, calcium was the lowest line. Then above it is magnesium. Then above it aluminum. Then above it actually you have aluminum, then titanium, perhaps titanium, then silicon and so on. Silicon, then manganese, right? So this calciothermic reaction or even magnesothermic. Very important, magnesothermic you may use this magnesothermic reduction, sir. This is very good. Magnesothermic reduction. Okay. Okay. So this over. This is one thing I tell you before I actually forgot to mention. So, let us clarify another point. Let us clarify another point we missed actually. But easy. Another point. So the lowest, the low oxygen potential is correct now. Low oxygen potential examples of, right? Examples of low oxygen potential systems are, tell me, which are low? Low is in the lower side of the diagram. Oh, I may forget today, just keep it. I may forget, you take it and you scan this page. So to take, or you may take it home and Xerox and return. So lowest is calcium. Then you have magnesium. Then you have aluminum, titanium. The one I do actually, keep it with you. Yeah. So what I'm saying, low oxygen potential system are examples of low oxygen potential systems are, tell me, calcium. Good, this calcium. So calcium oxide, magnesium oxide, or similar, tell me, aluminum, Al2, then TiTiO2, etc. Then perhaps silica, etc. Achha. Hence, this is why, okay, this is why these metals, namely, let me write, calcium, magnesium, aluminum, titanium, silicon, manganese, chromium can be used for yes, no, this can be used for deoxidation. Very important term in steel making. You are studying steel making. Oxygen is actually harmful. So for deoxidation purpose, namely deoxidation of steel, namely very important, deoxidation of steel. This is the interpretation or inference from this discussion. So that's why they are used. The lower elements, lower metals you will consider, namely this. Particularly aluminum, I tell you, aluminum is very important because, okay, magnesium is actually vapor pressure high, so difficult to use. Okay, calcium also likewise. Okay, aluminum, silicon are very popularly used. Aluminum, silicon, okay, manganese also, ferromanganese, ferrosilicon. These are good deoxidizer in steel. You studied this, and aluminum also. Okay, so these are the good deoxidizer because their oxide is stable, so they will remove and produce aluminum oxide. Okay, aluminum will, they form their own oxide, their oxides like aluminum oxide, silicon oxide, etc. Okay, like titanium also. Other can I do? Metallothermic is over. This is metallothermic. I will not consider. Next, here is give a star here. Similarly, conversely, which one? Upper metals are stable, are stabler. What does it mean? E.g., which are the upper metals? Tell me, give some example. I gave you last day. I tell silver, and iron is okay. Iron, even I'm giving this. Copper. I'm taking this. Say silver, copper, lead oxide, lead. E.g., these are stable. So it is easy to reduce their oxides. Because the oxides are not stable, so they will form the metal. So like say Eg, Ag2O2, Ag. Silver preparation is not difficult. Maybe costly, not difficult. Okay, you can see. Okay, I used to actually carry out this one in our lab, 460 Kelvin. And silver oxide, copper oxide to copper, lead oxide to lead, and also you can consider others. Okay, iron oxide also, but still iron will be little bit more difficult. Why? Iron is below them. Okay, the upper position. Okay, this is actually okay, this upper ones. Okay, so lead oxide to lead. This is easy. So you will easily follow. It is easy to produce copper making, for example. Copper oxides actually available plenty. Produce copper is not no big deal. That's why copper was produced when Bronze Age, 2000 BC. 2000 BC. Okay, iron later. Iron age is later. You see, this is the most actually primitive metal. Stone Age, first Stone Age no metal. Then came this Bronze Age, including copper later, and then came actually the Iron Age, iron and steel. Okay, Iron Age. That is also 1000. Okay, BC. It is actually about BC. Okay, but we are actually now AD. Okay, okay, very good. So this is actually some of the ramifications of Ellingham diagram or some of the discussion. Now, last thing that I will consider that I shall remove this. This is over. Important point I have said oxygen potential. Now I'll take up next question. So consider this. So consider refer to the Bronze Age. Bronze Age. Okay. So don't have to consider this. What is this actually I want to? Okay. Now okay. When right here, when copper was produced 2000 in 2000 BC in okay, let us take up okay this one, oxygen potential, oxygen next oxygen potential, oxygen and carbon potential, oxygen and carbon potential of a CO2 mixture, to find right here, to find the oxygen, oxygen carbon potentials of a CO2 mixture at a given temperature and pressure. CO2 mixture pressure of a given CO2 mixture. Says 60% CO, 40% CO2. What is the oxygen potential? Actually, before this, I'll take a of a CO2 mixture. Acha, the easiest now. Even I'll take up this, but recall. Recall. Right here. Just here. Note what is the oxygen potential? Oxygen potential is what? Potential is what's right? A activity O2 equilibrium. Write this by all means. in the system. At equilibrium means when the reaction has reached equilibrium, AO2. AO2 is nothing but, you know very well, PO2. Now you may ask us how these potentials we heard previously. Well, we heard chemical potential, I said. GI bar. GI bar is partial molar free energy, is also known as chemical potential. Recall that don't be confused, or you may, there is chance of confusion. Note previously considered what? Previously considered chemical potential. Mu, remember? Chemical potential? Mu I, which is nothing but, which is also GI bar. Which is also GI bar. GI bar is what? GI bar? GI bar is GI0 RT ln AI. We have picked up which one? We have actually shortened it, simplified it. GI bar is the chemical potential, but here actually we are not saying chemical potential of oxygen. You have to give the whole thing. But I am going oxygen potential. Then what will pick up? Only AI part. This is of course a function of AO2. GI0 plus RT ln AI2. So AI2 only simplified. AO2 means PO2. So what it will be? What it will be then? So answer this. Okay, say for your. So answer this. How we get this? CO2. Strike this equilibrium. CO gas. Write the equilibrium. Consider the equilibrium. Rather. Consider the equilibrium. Consider the equilibrium. What equilibrium? CO gas plus half O2 gas goes to CO2 gas. Happy? Again, you know delta G0 always. Delta G always there. So gives you K. I not. Gives you equilibrium constant. What is this? Tell me. PCO2 by PCO, activity of O2 means PO2. PO2 power half. Give equilibrium. Okay. This is at a certain temperature. Remember what temperature? The temperature is given at a given temperature T. So this is very easy. This is actually now ritual. So this is equilibrium. Now what is the PCO2 at a given pressure? So given pressure, you know, percentage, you know, partial pressure mole fraction gives you total pressure. Total pressure and mole fraction gives you partial pressure and gives you partial pressure. So what comes out from this? Obviously PO2 equilibrium. This is your answer to the question. So what is the equilibrium value? Sir, this value. Acha, very good. This part is okay. Now another, acha, this same example I am using. Find the carbon potential. Find the carbon. Next. Keep on adding. Next, find the carbon potential. Carbon means C. C potential. How to get this? See, oxygen potential involve oxygen. Then if you get oxygen potential, you involve carbon. Question.
In the previous line, why do you square it?
No, PO2 power. Right. This is okay though. This is okay though. This is okay though. This is okay. Then PO2 power. PO2 power half. You mean to say if PO2 power half is known, then PO2 is not known. I have to write this. I am not making a full-fledged calculation. From this you get PO2. Square, whatever is required. See, more this is that you do. This leads to PO2. Okay, happy to.
So then that will be that half will be reached, that power.
No. PO2 power half will be out. Okay.
Like we need to find out
Then PO2. The answer is see here. See what I have written. Oxygen potential is what? Right. You will find out PO2 power half. Then square it. Suppose 10 to the minus 6. Then what is PO2 power half is 10 to the power minus 6. Then what is PO2? 10 to the minus square of that. Minus 12. No problem. Okay, so this is the oxygen potential. Carbon potential of the same mixture. If you asked, with this equilibrium you will get this. No. You have to write an equilibrium involving carbon. So how do you get this? Sir, write this with the same CO gas, CO2 gas plus carbon solid. Okay. What is carbon potential? By the way, tell me what is this? Carbon potential is what? Tell me, you should note what is potential is the language. Mathematical form is what? Activity of carbon. Same way, write this. Active carbon at equilibrium. Never ever make mistake activity of carbon equilibrium. So do that. So K, again K, T is what? PCO2 activity of carbon, PCO square. Happy? Happy though? Okay. So KT is delta, again delta G0. PCO2 again you know. PCO square again you know. Because total pressure and percentage. So this leads to activity of carbon. This is actually equilibrium, remember. We are so smart by this time that actually carbon equilibrium. This is the carbon potential. This is the carbon potential. Achha, another question I'll ask you. Is any difficulty here? Here actually. So sir, activity of carbon can be less than 1. It can be 1, can be less than 1. Less than 1 possible. Okay. Less than 1 means CO2 carbon has not is not actually has not the same state as the pure solid carbon like graphite or diamond. Less than that, present with a less than 1 activity. If the activity be less than 1, there is corresponding to activity 1, there is a certain CO2 composition that you can back calculate. Suppose it is 1, then you can calculate what it should be. Suppose these are unknown pressure, you can calculate what, say maybe 80%, 20%. But when it is below that, it will be less than. Example of less than activity. What is the activity of moisture in this room? Just discuss this. Activity of moisture in this room. Okay. Now partial pressure, sir. Moisture is a gas. What is the partial pressure of H2O in this room? That is actually today's air composition. If you know, just maybe 0.03, etc. What is the activity of water, H2 moisture, with respect to liquid water? Now liquid water here. Liquid water is unstable. That's why it will be gasified. You keep water here, and after 1 hour, you say this is not there because its activity is not 1. So when it is at saturated vapor pressure, then it will be 1 actually. So that means if you increase the vapor pressure, then at time come when it will be the unit activity with respect to liquid vapor pressure. So the same H2O vapor. When H2 vapor is okay, what is this called? 1 activity of H2 vapor. I tell you. Remember, this is very interesting example. I tell you, H2 liquid you have taken in a what? In a container system, closed system, and it throws up some H2O vapor. This is the famous example of vaporization. What is this? Temperature is 69 degrees centigrade. I consider 342, na? 342 Kelvin. Temperature is 342 Kelvin. What is this pressure? Recall, what is the pressure? 0.3 atmosphere. You will get an answer to this. Very nice. Now activity, potential, carbon potential, etc. Here I am asking you one by one. What is in this system? What is the activity of H2? H2 I have said. The moment I tell you activity, then you should ask back, sir, with respect to what standard state, sir? Has no meaning without reference to the standard state. When there is no doubt, then actually fine you can. But you should, by all means, should actually refer to the standard state. I am giving you activity of H2O with respect to vapor phase, gas phase as the standard state. 1 atmosphere H2 as the standard state. What is the answer? What is the activity? Gas. What is the gas? What is the activity? Partial pressure. Remember, partial pressure. 0.3 is the answer. So activity of, shall I write this part? Activity of H2O with respect to 1 atmosphere H2 as standard state. I am taking this here from here. These are all over. So I'm just carrying this for some activity of H2. I'm saying. See what I'm saying? Not water, a vapor. H2 with respect to vapor. Is okay too. Is okay. 1 atmosphere. What is the standard state for gas? Standard for gas 1 atmosphere. 1 atmosphere H2O as standard state, gas as standard state. Then what will be your answer? Your answer will be, sir, nothing but pH2O, which is 0.3. And unit? No, activity cannot have any unit. It's divided by. So 0.3. Now same system I'm asking. Referring to the system, H2O with respect to, is it 1? 0.3 is okay. It's okay too. 0.3 is okay. I'm giving okay means we're satisfied. With respect to liquid water as standard state, another standard state, one is gas, another liquid. Liquid water as standard state. Then you will understand this as standard state. What is this? To H2O. What is the standard state? The pure liquid is existing. So, sir, nothing but one pure liquid water, pure water, pure liquid. This is the difference. Okay, see, water with respect to what? So I said what? It is not one. Okay, what is the chemical? What I said here? Carbon potential. What are H2 potential? H2 potential is how much here? See, with respect to this, okay, activity of H2. The moment I said activity means related to standard state. So suppose this I said activity is how much it is? Okay, with respect to this point. This is the H2 potential. What is the H2 potential? Carbon potential. H2 potential. You can use this. This is a 0.3. Okay. H2 potential with respect to 1 atmosphere as the standard. Okay. 1 atmosphere H2 as the standard state. Okay, very good. So this part is okay. Over. So anyway, you have understood that this is how you get this. Okay, this is you get this. Okay, carbon potential. Similarly, you can have what others you can get. Carbon, oxygen. You can consider sulfur potential, sir. Example of sulfur potential. What is the reference? Okay, sulfur potential right here. Remove this. Remove this. Sorry, remove this. Similarly, sulfur potential. Similarly, sulfur potential. H2 potential, chlorine potential, nitrogen potential, such thing. What is this? Say that means suppose H2S, H2 gas. What is the sulfur potential? Activity of sulfur. Sulfur potential means activity of sulfur, sir. Activity of sulfur means pH2 sulfur. Okay, 1 atmosphere. When I say activity to partial pressure is for gas phase, means 1 atmosphere as the standard state. pH2 is what, sir? You have to strike equilibrium. So now tell me, suppose H2S, H2 gas. Follow, clarify. What kind of questions can be asked? Sulfur potential, you have said, sir, is understood. What else can be asked from this? H2S, H2 gas mixture. What other potential could be possible? Hydrogen itself. H2S. Actually, normally I will go by the element. Although I gave water here just for some other reason. Hydrogen potential. Okay. Similarly, how you get this pH2? You strike the equilibrium. H2S anyhow. H2 plus half H2. You get this. K is you get this. Similarly, K is dot. I am not giving you. H2S H2. So hydrogen potential you want to same equilibrium use this. Same equilibrium use this. Achha, by the way, you answer this question. I will be very happy. Suppose 80%. Very interesting question. 80% H2S, 20% hydrogen. One atmosphere system, and temperature is 1000 Kelvin. I ask you, what is the sulfur potential of this gas? So what you do? Starts involving sulfur. Sulfur means H2, remember. Involving sulfur. So right here, H2S gas, H2 gas. So get delta T0. I'm not saying all these things. So what is this? pH2 power half pH2S. Happy to? Equilibrium. Now 80% means partial pressure is known, pressure is known. So you give a tick mark, pH2 out. pH2 out. This is sulfur. Power half means okay, you can get square it again. Okay, answer. pH2 potential, sulfur potential. Question is, sir, I can ask element wise if you go. Typically you go carbon potential, oxygen potential, nitrogen potential. Here I said moisture just to put an analogy. Okay. So anyway, what is the hydrogen potential? If I ask this gas mixture, say another question. What is the hydrogen potential? Sulfur potential calculated out. You calculated delta G0 to K, etc.
Similarly, we can put the values of pH to and then
Yes, I can write this. If you ask me, I will put this. I put what I will put. Tell me. Suppose this is the question. You tell me. I will do whatever you ask me. Okay. This line H2S 0.8 and hydrogen this. Then what shall I do? Yes, I substitute this and this. If you substitute, I will get. Then my question is not sulfur. It is over. Hydrogen. Fallacious. Sir, you have already given, sir. What foolish question you are asking us, sir? Do you think, sir? Sir, what you said? What is it? Went to hydrogen. Sir, given, sir. Sir, partial pressure of oxygen. So this room, what is the partial pressure of, what is the activity of, what is the nitrogen potential in this room? Now, partial 100% activity of nitrogen, sir, means partial pressure of nitrogen since gas. What is the partial pressure of nitrogen? Is partial pressure 0.79 atmosphere. Since actually activity it is, so 0.79 is the answer. This room. Thank you. So potential part is over. Another last, actually I missed this. Can I finally already note, we already have considered the original one. That actually I found. Note already consider. Tell me the oxygen potential. Oh, sorry, sir. Oxygen potential of a metal oxide system. Of a metal oxide system. Let me write this way. Of a metal oxide system. Remember this? This we begin from this. I told you na? The lower oxide means smaller oxygen potential. Smaller. Lower oxide means smaller. So oxygen potential material. What is this? What is oxygen potential for this? Actually, the lower one has a smaller, but there should be rule actually, no? So this is you cannot remember this way. Mathematically, quantitatively, what is this? Answer is, sir, PO2. Oxygen potential means right here, PO2 equilibrium, write this by all means. Then strike the equilibrium involving oxygen. All involving oxygen. So metal plus oxygen is metal oxide, sir. I'll write this. Delta G0 leads to K. This you already done actually. AO2. AO2 you did. This is how you got the PO2. Is AMO2, AMPO2. This being pure, you have implied is pure actually. I cannot write so many things here. 1. So 1 by PO2. Hence PO2 is equilibrium is out. This is oxygen potential of this system. What is oxygen potential of AO2 in the previously the first one? Today, what was the oxygen potential? What will be your answer for AO2 at the temperature T1? Today, at the beginning I discussed. What was the oxygen potential? PO2 equilibrium. What is value? 10 to the minus 12. These are assumed value. Though assumed value. This is the oxygen potential. Also equilibrium partial pressure of oxygen. It's okay though. Enough is enough. It's okay. So this part is over. Last is, I will tell you, carbothermic reduction. This is actually more important than metallothermic. And bearing example is what? You know very well. Blast furnace itself. Blast furnace. So next, carbothermic reduction. This is very popular term. I am giving you example is blast furnace and DRI. You have read direct reduction, e.g. blast furnace, DRI reaction. I am writing DRI. Directly reduce iron. Okay, I am not writing it. So carbothermic reduction. What is the very interesting? Carbon, when it comes carbon, I am writing you. Tell me. I tell you what. We want to reduce our objective is what? We want to know the temperature at which carbon will reduce will reduce oxides like difficult oxides, relatively stable oxide, but we have to prepare them. All metals and metallurgists should prepare. All metals, lower, upper, middle, all. So oxide likes what oxides? Like I tell you, aluminum oxide, you know very well. Another TiO2, silicon. These are very popular. Okay, silica is actually available plenty. You know, titanium is actually very useful metal, and aluminum is also this. Then how do you proceed? Again, delta Ellingham diagram. Same logic. Actually, easy. Delta G diagram quickly. So I'm drawing the three lines. You just consider this. Please consider this. Please consider this. Three lines. This line is should be parallel. Why parallel? Last day I discussed. Remember why roughly parallel. Remember those classes. Those who have missed actually should go back to that one. Okay, this is not bad. So right, what is the top? Lowest is what? Yes, aluminum. Right, this is aluminum oxide system. We say like alumina oxide system. There's titanium dioxide, and silicon. Carbon line is where? Carbon will reduce. Okay, carbon line is what? You know, CCO line I am drawing. You may object, but let me draw this line. This is CCO line. Okay, but remember this is actually standard state line at under 1 nanosphere. Okay, so first answer you give. Your teacher will invariably ask you go back and from the Ellingham diagram tell us you have to your project is to produce titanium by carbothermic reaction of titanium dioxide. This is the project. So what temperature? What shall I do? Sir, go to furnace. Which temperature, sir? Now clue you will get from the Ellingham diagram. What is the line? This is CCO. I give you the answer. So this is C. This is C. This is the I'm writing. T E I'm writing E I'm the language I'm using, so although everything is T silica. This is T silica temperature, right? This is temperature silica, and this will be what is the meaning of this first of all? So you want to reduce silica, produce silicon. Silicon, you know, silicon industry is actually very useful to us. Silicon from silica. So what temperature you will use? See, remember that. What is the competing oxides here? Consider only silicon system and carbon. Competing oxides CO and SiO2. And metals are what? Silicon and carbon. So which will what temperature? They cut across at this temperature. Your answer is very easy. What will say? Any temperature greater than this, then what will happen? This oxide will be lower and that oxide will be stable. So carbon can reduce silica at beyond this temperature, above this temperature. This is the answer. Okay. Similarly, any temperature above. So I'm giving this, you understand. Any temperature above, get silicon. So what is the corresponding line for TiO2? Now any temperature greater than this. Below it cannot. Carbon cannot reduce. Okay. So you will set your furnace temperature likewise, and this will be T alumina. And you see clearly that temperature requirement is gradually increasing with the stability of the oxide. See, more stable, then greater temperature is required to reduce. Now, one question here. Okay, one question here. These discussing is okay. One question you may ask, why not CCO2 line, sir? CCO2 line, remember last time I discussed this? CCO2 line is like this, you know, almost flat line, CCO2 line. Why you have not considered this, sir? This almost will not attack this. Actually, you have to, at high temperature, this you should note. Another point. Recall, high temperature CO is the stable carbon saturated system. Add this in a carbon saturated system. Recall at high temperature, low temperature, you should consider CCO2. Then you say which is low, which is high, sir. It is up to you. Then, which is high, then it is best. I can handle both. Say medium temperature best. I address both of them. Then you have to consider CO2. Complicated though, but that is the challenge. That is the understanding of thermodynamics. Yes, sir, anything that I can do also. But today I am not discussing on Ellingham diagram. A simple thing I am discussing but if it is a CO2 mixture, you consider accordingly. Acha, recall in a carbon saturated system, CO2 is stable at low temperature. At low temperatures, what is this temperature? I told you 400 degrees centigrade. Remember, 673 Kelvin, and in a carbon system, CO2 is stable. In a carbon system, CO is stable at high temperature. It's stable. I'm very sorry. It's stable at high temperatures. High temperatures, namely T greater than 1000 degrees centigrade. T greater than 1000 degrees. What is this? 12. About 99.9%. Okay, it will never be 100%. Impossible, just impossible. Similarly, it will never be 100% there. So this is actually your, this is like this is. So now, since we will actually know this will be possible at high temperature, we consider that it is a CO line. Will be pertinent to us, not CO2 line. But if it is a medium temperature, then actually you have to consider this actually that you have to, you can solve it. You can solve this. This is actually thermodynamic problem. So many problems we have solved 11 and another coming. Okay, another series coming. So this is 1273. This is actually, that's why I have considered this line. So this part is understood. Okay, so any temperature you can get this reduction. But note, however, the shortcoming of Ellingham diagram. Of the Ellingham diagram. What is the shortcoming? Main shortcoming is what? Main shortcoming, that is, it considers a standard state only. Standard state, that means if you, it consider the standard state conditions only. Under non-standard state, what will happen? You have to, for non-standard states, one has to modify Ellingham diagram, which you don't get. You have to do yourself, perhaps. One has to modify the Ellingham diagram. Okay, so this I'll show you now. This I'll show you. Follow me. Okay, consider this very interesting problem. You just go through this. Well, so I'm again delta G0. Always consider this delta G0 versus T. I am actually drawing this line. I'm drawing this line. CCO CO2, no, it will not be any problem. Okay, CC, it can be CCO2 also. This is a CCO line. Delta G versus T. And what is the titanium line? I'm considering based on this. This is my titanium oxide line. That should be better drawn. In a better way. This is TiO2. A moment ago I discussed. So what is this temperature? This your answer is what? Where under what temperature carbon can reduce titanium dioxide into titanium dioxide into titanium? Any temperature greater than this. I am right. TE1 for some reason. TE1. And if you ask me what is this temperature, perhaps I calculated myself. Okay, it is 1987 Kelvin. Remember, large temperature. Okay, high temperature. This is about above 17 degrees, 100 degrees centigrade. Okay, so for this you need actually very, what is called, supercanthal furnace, molybdenum disilicide heating element. Difficult though, but this is the, since this is actually this. Okay, this is okay. That means at what temperature the reaction will occur? Tell me, as you know, any temperature greater than that, reduction will occur. Okay, but you suppose you want to work at a lower temperature, affordable. So then what you will do? Right here, this time 1 nanosphere for some reason. This though, then suppose, then you actually draw. I draw another line. This line is for CCO 0.4 atmosphere, not 1 atmosphere. Okay, this is actually added to the Ellingham diagram. So now you see which temperature, which is the cutoff, which is the cutoff temperature. this. Now smaller than this, so you can actually afford to have a T2. This temperature I can tell you, I know this also incidentally, 1908 Kelvin. Okay, so now you see, so this happens actually. CCO, lower pressure. So what's the use of using this non-standard state? What is the purpose of using this non-standard state? This is actually vacuum operation. 0.4 atmosphere means vacuum operation. So here at a lower temperature, suppose you have a furnace running at, say I tell you, for example, 1950 Kelvin. Then what will you do? 1950 Kelvin. Can you work at this 1 atmosphere pressure? That means you can just draw this figure easily. I have taken in a board in a titanium plus carbon, and what is this outside is what? 1 atmosphere. What temperature? Temperature, tell me. 19. What temperature? Yeah, suppose I write here. Okay, what should I give this? Working temperature. I may use this. Right. Or this will be better. I have to use no way. I'll show here. Draw this. This is your working temperature. T1 is what temperature I said? 1950 Kelvin. Working temperature. Your furnace. Just consider an example. So at 1900 Kelvin, is it possible? Ball. Is it possible? Working temperature is what? 1950 Kelvin. Is it possible this? Typically, people will consider 1 atmosphere open atmosphere, like this. Maybe gas bubbler is there for safety, but is possible? No. So see, you see, at this temperature, which is above, say 1 atmosphere means this line rather than this line. This line means this is above and titanium is below. So above, below, the titanium oxide is stable, sir. So no reaction possible. But if I write once more to actually clarify this point once more, otherwise same, right in a bigger way, titanium oxide plus carbon powder. What you are put a vacuum. Pressure is 0.4 atmosphere, right? Vacuum. You have set up a vacuum here. Now temperature is same, 1950. Your working temperature, right? Reduction is possible. T2 reduction, I write. Let me write. Reduction. Achha, right. Reduction is possible. Sorry. I will actually consider 3 critical things about this. Three. See, you have understood this part. This is okay. Though. One thing you see is very interesting. Those actually first you tell me, sir, very good. 0.4 atmosphere, why is moved this way? See, every point you can ask actually in thermodynamics. That is the whole problem. You say, why not this other way, sir? How do you know? How do you know that this has a steeper slope? Why not a flatter slope, sir? Then it will be otherwise. Other way around, that it will be, it will not. Either case you will not get. Why? The first answer, sir, why steeper slope? This part, you just consider this. Let me remove this. This is actually some additional discussion. Then I will give you the punchline of this. See, what is this? Why question? Why steeper slope with CCO 0.4 atmosphere line? Then obviously CCO 1 atmosphere line. Okay, this is the question too. Sir, why not? Why not other way, sir? 2 questions I ask. Okay, one way. Question 1. Question 2 will come soon. Okay. What is the slope last day? What is write this? What is the reaction? Write this. See, I'm writing actually. Main thing I'm writing. C plus half. C plus half O2. Let me write. What is this line? C plus. Write this. Right. C 1 nanosphere, standard state. Pure, I'm not writing. Half O2, right? Half O2 oxygen is standard state, means 1 nanosphere. Good, very good. Is CO 1 nanosphere.
Sir, it will be only O2, 2C plus.
C plus, good. No, 2C plus O2. Oh, very good. What's, yes, very good. I made a mistake here though. Okay, what shall I write?
2C plus O2, you got 2C.
Or can I write C plus? You cannot write this though. I can write. Why can I cannot?
Because it's
One more.
Ellingham diagram must be one mole. But since this is actually being considered, so what is this reaction by the way? This is called what reaction? Yes. No, formation. What is formation of CO? Formation of CO. So Ellingham diagram. This I also discussed actually the difference between Ellingham reaction and formation reaction. When one, you know this very well. Okay, happy though. So this is one line. And what is the second line? This is CCO2 1 nanosphere. CCO 1 nanosphere line. Full elaboration is this, okay? And second is CCO2, sorry, 0.4 nanosphere line. What is the reaction? Can I write? Write it nicely. What is the reaction? See, right, similarly, which has changed? See, we don't change at other places. On. What has changed? CO has went the second line. It is purely standard state line. It's standard state. This is a standard state line. Standard state consideration. Standard state consideration. I mean, all states are standard state. Remember what is the standard state reaction? All states. No. Nothing should be. Okay. Okay. Nice should not be. Should be without. Okay. This. Okay. Standard state consideration. Left hand consideration. All state standard. This is what? This is should be non-standard state. Non-standard state consideration. No state cannot be. Can be actually. What is this? This excluded. All states should be included. All species should be standard state. But here, this is standard. This is standard. One non-standard. So this is non-standard state. Finally, what is in this case? What is this? Please tell me what is this? In this case, delta G is what? Just I'm not writing. What is the delta G? Is as good as delta G0. This is delta G is not delta G0. Achha, by the way. Now steep slope. What is the slope? Please tell me. Now follow. Slope is what I told you. Achha, good. Minus delta G. Recall. Achha, first of all, get this delta is 0. First case, delta G0. Achha, 1 and 2 I am giving. This is 1. This is 2. Delta G0 1. Delta 0 1. Quickly tell me. Tell me what is this? Delta G0 right fully. Product, standard state, reactance, that all you have to write in terms of entropy now. S0 quickly. S0 CO 1 nanosphere. Write nicely. Achha. Now I am removing these lines. Shortcomings we are discussing. S0 CO quickly minus. Tell me. Delta S0 is what? Product minus reactant are all standard though. S0 CO, S0 C solid, solid 1 nanosphere, right? 1 nanosphere solid, 1 nanosphere minus. Right? So all remove this. S0 O2, good boy. Half of S0 O2. No, half where? It cannot be half anymore. Why I wrote this? You told me, but still I written this suddenly. Okay, 2CO. I am very sorry. 2C plus O2 is 2CO. Very sorry. I am very sorry. So this is happy though. Non-standard state consideration. Non-standard state consideration is what? 2C plus O2 is non-standard state consideration. What is this? 1. Please write. What you write here? 2. You write 2 minus 2 S0 O2 1 nanosphere. This is your standard state. Delta H0 also. 2C plus O2 is 2CO. Thank you so much. Achha, delta is 0. Good. Very good. Delta is 2. Second case, right? Similarly, right? Which these terms are not affected. Minus these terms are not affected. The term affected is S0 O2 what? Now think about this. Now we'll get the answer. Second question will be even more involved or even more tricky. First, let me complete this tip slope. So delta is 0 okay to? Huh? Now tell me which is greater. Here see, don't compare. These are same. These two are same. About consider about this. Which is greater value? S0O2 0.4, S0O2 1 atmosphere. It cannot be S02. So you write it should not be in principle S02 because it is not standard state. So it should be SO2. Okay? This okay. Now which has greater value? Same value. Now entropy as a pressure. Remember what is the how entropy of a gas? It's purely a gas system. What is the entropy of a ideal gas? Entropy of ideal gas is what? Delta S is what? And same temperature, RLN V2 by V1. Remember, RLN plus CBLN T2 by T1. Since constant, same temperature I am considering both of them. So RLN V2 by V1. This is actually remember related to RLN P1 by P2 at opposite isothermal condition. So means which is greater of this pressure? That means volume increases, entropy increases. Means pressure decreases, entropy increases. Whose entropy is greater? And it's a minus sign. So delta is 0, it increases, decreases. So delta is 0. So write this. First of all, write this. Delta is 0.4 atmosphere is greater than SO2 S0 to 1 atmosphere. Happy though. So what does it mean? Delta is 0 2. That leads to I don't have space. Delta is 0. Tell me 2. What you said? Tell me. Delta is 0 2. This is greater. Negative means greater means delta 0 2 is less. I should remove the term 0. Delta is 2. Because not standard state. All species must be under standard state. Then that is a standard state reaction. Nothing can be actually barred. Okay, so this is okay. So delta is 0 2, delta is 0 1. What is the slope? You have written. So that's a slope that indicates. Shall I write here? Can I take this? Slope of 2 second line. Slope is negative. These are what? These are positive though. So delta is 0, positive, right? Positive. These are positive though. Delta is 0.
Delta is not positive. Sign will reverse. Sign will reverse.
Delta. So right here, slope 2 will be. Delta is 0 2 is greater less than. So slope 2 will be greater than. No, I'm telling you. So see, follow this.
Delta is not negative.
More positive. Right. This is not only positive, negative. Right. Please follow this. First of all, tell me. Okay, this is. So I'm writing. Please let me write this. Delta. Shall I write here? Right. I have to write here. No way. Delta is 0. Please tell me. Delta is 0. 2 is more. Follow me. Is more positive. More positive than. Will accept this statement detail. Delta is 0 2 is more positive. Positive means slope negative. That is coming. So, but it is more positive. Why? Because it is negative. Is actually negative. This is which are this is higher entropy though. So delta is 0 2 is greater. Okay, slope. It should be is 0.4. This has a what? Less pressure means is higher entropy. And delta is 0 2 has a. Now, first of all, this is positive. So these are positive because this has no entropy. This is positive. This is positive. Delta is 0 positive. Both are negative slope. This now tell me, this is 0.4 atmosphere means what? Pressure. Oh, this is what? These are more. Which has greater entropy? This or this? Pressure decreasing, entropy increasing. So this has greater entropy. Let me write here. This I have written. This has a greater entropy. This I have written also. This has a greater entropy than lower pressure, V2 volume increasing means pressure decreasing means greater entropy. Achha, if it is so, then what is happening? Delta S2 is more positive. Is it okay? Delta S0 is greater. Slope is, huh? Acha. No, this should be actually clarified here. No, coming to this. Slope is have I made any mistake anywhere? Okay, this is correct. This is correct. This is greater. SO2 is, oh yeah, you are so nonsense. I am nonsense. You are also. Who is 0.4? Oxygen is 0.4. Thori. Oxygen is 0.4 atmosphere. I have written that. Oxygen is 0.4 atmosphere. Oxygen 0.4 is where? CO. So what should I write? One atmosphere in each case. Nakide. This is S02. You can add. Who is changing? That's why this is making 0.4. Nakide. This is okay though. Now at a lower pressure, there is a greater entropy. So this is, it is more positive. Now it is okay though. It makes sense though. This side is out. Same. So this is more greater. So this is more positive. Okay. This is more positive because entropy is positive always. All entropies, zero entropy is when at 0 Kelvin. Third law. So more positive. Then what is the slope? What is the next? Is tell me. You fix this line. CO, and it is, why not standard state? Why not neutral? Why not 0? Why not 0 here? Superscript 0 here 0 because it is 0.4 atmosphere. It is not good actually to write this. Okay, non-standard state to give a superscript 0 not acceptable. Okay. Anyway, so delta S2 is more positive though. So what does it mean? Right here, shall I write? I don't want to. Slope is minus, since slope is minus, I should have written here. Slope is minus delta 0. Slope will be, slope 2, tell me, will be more negative than, and which you have got? Happy though? Some explanation. Last is, and why they are actually, see, slope has changed. Actually, continue, complete this. Complete this. Interesting question. You answer. This is maybe the last question, last but one. Okay, then this topic. But they have started from the same. Somehow maybe wrong or right, I don't know. But actually, it has been originated from the same point, but with different slope. Why this happens? What this point imply? Remember what this? Remember this temperature, though it is actually should be dotted line. For some reason, because 0 Kelvin. Intercept is what? At delta G, at T is 0, the value of delta G0 is the intercept. Y is mx plus c. What is the c? Value of y at x is 0. At value of y at x is 0 is the c, the intercept. So 0 Kelvin, but since 0 Kelvin is not attainable, so give a theoretical interpolation. Okay, happy to. But this is given here same point. I will draw this. Initially dotted, but then no problem. Why? What is? I am helping you. Why? What does it signify? This is delta. Is it delta? What is the relation? Tell me. Minus T delta is 0. Remember? So delta 0 versus T. Slope is what? Slope is, tell me, minus delta 0, and intercept. Intercept is what? What is the intercept? The value of delta G0 at T is 0. That is the intercept. intercepts, you are not considering 0 and intercepting it, then that is not the value. Delta is 0. See, but this happens to be same. Intercept is what? That is value of delta G0 at T is 0. T is 0 Kelvin. Happy to? Quickly. I've given you. So why they are not different? Delta is 0 changing. See, two lines are different. One is CO is 1 nanosphere, another is CO 0.1 nanosphere. Other things same. CO is 1 nanosphere and 0.1 nanosphere makes a difference in the slope, means the entropy. Entropy changes. Constant entropy now. Entropy has changed, sir. Enthalpy has not. What is this? Delta G0 is okay, all the time changing. Okay, here also, no problem. What is the reason? Again, you follow. I'm helping you. I'm guiding you. You follow. Again, this way, instead of in your mind, inside your head, you say, think it is all H. H. H, H. H. Again, same. Again, here. H0 up to 1 atmosphere. H. What I'm writing? Who wrote this one? Okay, sorry, here. These two are same. Here. 2 H0 CO1 atmosphere and 2 this will remove 2, sorry, this will remove 2 H CO 0.4 atmosphere. 2 again common. So H0 CO 1 atmosphere versus, if I may help you, you consider this. H0, I'm helping you. 1 atmosphere pitted against HCO 0.4 atmosphere. What is the comment? A moment ago, these are when it was entropy different. This enthalpy. If they are different, then it should not come from same point. But coming from same point. Entropy different. Energy also different. All the points you see different points. Any question? Any answer? If you can answer this, then we will understand that you have actually we have some good grasp of the subject. Previous discussions. Okay, you have actually good memory and we have retained those ideas. I'm helping you further. Gases, you consider which type of gas? Real gas or ideal gas? Obviously, consider ideal gas. Real gas, then real liquid fugacity, then you have to give this. Ideal gas, I have considered many times actually here, maybe. See, any ideal gas. Give an ideal gas, then any idea? CO is behaving ideally. All gases we have considered actually, you see. Okay. Then ideal gas, an ideal gas at 1 atmosphere, an ideal gas at 0.4 atmosphere. And the temperature, what I said? Same temperature I consider. Temperature is entropy, same temperature I consider. Enthalpy of an ideal gas, first days, introductory lectures, is independent of pressures. Isothermal process, that's why delta H is 0. Isothermal process, what is the delta? Isothermal process, that. See, what should I say? This figure coming back. Isothermal process. Ideal gas, isothermal process. You have a total gas of this. Enthalpy has not changed, 1 to 2. Because pressure has changed. Temperature has, isothermal temperature. See, it depends on solely temperature. So temperature has not changed, pressure changes, so what? So nothing will happen, sir. Same enthalpy. For ideal behavior, considering ideal behavior. Consider. Leave it this point, okay? Is okay? So yeah, anyway, these are actually, now at the end, I tell you something very interesting. Here. This is the end point. Remove this, remove all this, you remove, sorry. It took help. After all said and done, I should say, you will perhaps not use Ellingham diagram, except for quick idea about which temperature this will cutting across with carbon. Let us quick, because you don't remember so many things. Let us actually live through these pages. Okay, yeah. So this will, but detailed analysis how will get? This is actually you want a quantitative answer, which temperature, etc. So what I tell you, I'm taking up this. Okay, this one. Say you have to rely upon we have to rely upon mathematical analysis of the problems. For example, e.g. what vacuum, I gave you what pressure, what vacuum is required. You now reconcile everything, that how much Ellingham diagram is used. Who will draw this for you? Who will draw? After drawing, your question, your problem is practical. You have to actually solve a problem through the semester, okay, using the semester. Okay, so what vacuum is required to reduce titanium dioxide at what? See, one, what is it? What is this? At 908 Kelvin. I am giving you. First of all, you answer the why it is, why 1908, it is 1 atmosphere will be all up. Normal pressure, you have already seen that it is not possible. Okay, so non-standard state, vacuum. This problem, can you remember this problem to anyone that was solved before? What pressure is required, vacuum, how much vacuum is required to reduce magnesium oxide into magnesium and oxygen? Problem 2, problem 2, 3, 2, 3 or 4 maybe. 3, 4 is practice problem. 11 practice problem in series. Third problem. So what you will do? So who will give you these graphs and you do the graph? Draw the graph first. No, analytically solve this quickly. How to solve this? See, this is how actually answer solution. You just take a problem. Take this problem. See, no, don't have to look back. You will see magnesium oxide. Remember, I spent some time MGS, stoichiometry, etc. This is even easier than that. Why? You write pertinent, right? The pertinent equilibrium, pertinent reaction equilibrium, what? Is what is? Tell me. Required to reduce titanium by carbon, by carbothermic reaction. To reduce carbon by carbon means carbothermic. By carbon at 1090. What is the answer? TiO2 plus carbon is Ti plus. You don't have to consider. We are forgetting Ellingham diagram. You don't know. You have not learned Ellingham diagram. Solve this problem. TiO2 plus 2C is 2CO. Delta G0 will be available to. Delta G0 will be available. A plus BT. You know though. Is the data is such that delta 0 1908 is how much? Will be positive. You can check this. It is positive. Okay. It will be positive. Okay. That's why this has happened actually. Although this, don't worry this part. Okay. Very good. Okay. Okay. So positive. That means what immediately inferring? You are inferring what you are inferring immediately. Under standard state you will not carry out. So vacuum. So the question of vacuum comes. Means standard state impossible. Standard state means one impossible. 1908. You know, this is possible only when cutoff temperature was 1987. So above that. So below this question, so not possible. You know, this also shows. So you appreciate the problem. Oh, vacuum is required. Actually, you have to reduce the activity. Right hand side told you na, to make a reaction possible. So this is impossible. Uphill. So make it not only flat, downhill. So reduce the activity. What is how to reduce the activity of a gas phase? By lowering the pressure. This is easy because solid is not possible. Solid activity, okay. So solid pure is activity. So this is quick answer. So all are actually consistent. So you say now okay, what is the vacuum record? You write, apply this. It's called delta G0 19. I am very sorry, I am repeating this as a positive is what? Is actually leads to K value, K. How to solve this problem? Quickly. ATI PCO square, ATiO2, AC. This is the answer. Equilibrium. What temperature? And 1908. This is known to Nakire. This is known. Delta G0. Data book. Okay, known. Equilibrium constant. Delta G0 is minus RT line. Shall I write this? How many times I shall write? Happy though? Quickly, tell me. What else? What simplification you expect here? Tell me. See the reaction. You have taken titanium oxide pure.
Carbon is one.
Carbon is you have taken one, graphite perhaps, or titanium will be produced pure. This time it will produce pure.
PCO square equal to
So PCO square is out. So is PCO. PCO will be what? It turn out to be what you know. If this calculation is correct, and perhaps I have done this myself. So what it will be? 0.4. Is it corresponding this? What pressure? Is it this line? 0.4 line. So this will be 0.4. You can check this. You can check yourself with the data. Check yourself. What data you need? Let us you want to say you are not suspicious about this. You go back home. You just solve this problem yourself. So what needs a delta G? Everything else is given. Delta G is data book. So which data you will look for? Tell me. Data book typically gives formation reaction. They don't give a ready-made delta G. How many they will give? Formation you combine in any form, anyhow. So what is the what you will search for?
formation of titanium and
Never ever.
sorry, CO.
CO and TiO2. That's it. Means C plus half O2 is CO. Formation reaction. Then you consider forget about Ellingham diagram now. Formation reaction, C plus half O2 is 1 mole CO and 1 mole TiO2. Okay, so go back home, no problem. Go back home, no problem. You can check also. You can, in case you need, you can take data from me. Okay, very good indeed. Now answer. So over. So this is how you got this answer. So what vacuum you will use? So PCO is points up. PCO is the only sole gas. So this is the total pressure as well. So that is P total is what? PCO is 0.4. So what will be the answer? Tell me. Means this cutoff. See, this cutoff is signified by this. Okay, by this calculation. Calculation of cutoff. Cutting up, is it what temperature is actual back calculation. I'm trying to find out 0.4. I drew for 0.4. I found it is intersecting at the temperature of what temperature? 1908. I consider 1908. So no problem, sir. They are pretty consistent, same thing. Now, what will be your answer? So tell me what answer? What vacuum will you use? 0.4 is a critical, not less than, even less. Just less means this side this will be just does not, you see, if it is even with the lowering of pressure it will shift to the further, it will shift to the left, so it will make it possible. Okay, it will just exactly. So your answer is either, so let me finish this first. So your answer will be less than. You see magnesium oxide problem, less than calculated 0.06 10 to the minus 10 or low pressure, then we answer less than that. Otherwise not. This is still equilibrium. You want to make it spontaneously reduce, continuous. All that you maintain that all titanium dioxide will be reduced, provided you have given carbon enough. That you will give. Yeah. Okay, so alternative answer. Suppose 0.4 nanosphere you have chosen. Yeah, this vacuum operates nicely for 0.4 nanosphere, sir. Sir, I have chosen 0.4 nanosphere. Then what temperature you want? Again.
8 or greater.
Yes. 8 or greater. This is the right answer. 900 greater than that. Is 900 exactly? They are in equilibrium. Delta G is 0 actually, type of thing. Greater than that. So shall I write these two lines? These two lines I am writing. Okay. So 0.4. Can I hear? Can I hear? Stars. So too many stars. Okay. Triple star maybe. These are the last two lines for the Ellingham diagram and this chapter. I'm sorry, I thought actually I'll solve some problems. But in any way you have completed satisfactorily, more or less. So vacuum required. I'm answering the problem. So the vacuum required. That's a Nirja. Why vacuum? PCO is 0.4 atmosphere. Vacuum means the vacuum total pressure. Total less than 1 maybe, but total. See, it doesn't know. The pressure maintained. Why it is vacuum? Because the pressure under which the system is exposed to is running. Because PCO is the only gas. So vacuum the total pressure, and that's why I wrote here. PT also there. P2 is point. So this is also, since it's less than 1, that's why we call it vacuum actually. So, but this is the total pressure. So vacuum means covers the vacuum pressure is the PCO pressure. Okay, so vacuum required is bolo PCO is less than any value, right? Any value will be any value, any pressure, vacuum required any pressure. This answer is over. Less than, underline, less than 0.4 atmosphere. On answer. Note, I am removing all this, since you have got this. Note, alternatively, you may say, you may comment what? Tell me, yes, Anurag nicely answer this. What? At a comment that at a given vacuum of, at a given pressure or vacuum, pressure here, since it is less than 1 also, it is vacuum. At a given pressure or vacuum, interchangeably, of 0.4 atmosphere, I am fixing it, 0.4. The temperature required, the temperature required for the reduction of TiO2. I will remove this line. This should have not been removed actually, no? Since some people, well, they may look back, no? Easily, no? They may look back here. No? It's actually, I say here, this line, at least this line is under discussion. Okay. What temperature is this? Tell me. 19? Good. It's CCO. This line actually went astray. So it's not linear. CCO 0.4 atmosphere. This line is good enough. This is TiO2 line. Sorry. Okay, CCO. Very good. These two lines are actually competing here. So at what temperature? The temperature for the reduction of TiO2 is right. This is greater than any value. Any value that is actually mark that. Any value greater than what is temperature, I should say? 1908 Kelvin. This concludes our discussion. This concludes our discussion on the Ellingham diagram and its paraphernalia or its related things. So this is over. I will actually, can I have some time, 5 minutes or 10 minutes? How much time? Yeah? 47. Just one problem actually. This over. I will now take up assignment number 7. It is better actually. Otherwise it will be actually. So I discussed in details. So quickly remove this. No, this is actually unnecessary. Simple. I thought actually 2 problems will be solved, but today one stress. This look at it. Look at it. Okay, everything okay.
It is now it is okay, but it may turn off.
Okay, it is already turned off.
No, it is
Okay, so I mean, one problem is if there is any difficulty, let me know. I will repeat that next time. One problem, very easy problem I am taking for you. One problem, you will enjoy this. First of all, say note assignment 7. Assignment number 6 over 7. I didn't give you actually, but this is I am discussing this. This assignment is quickly. Let us see how quickly we can answer this question. Calculate. I am writing here. Since one problem I will discuss only, I am writing on the top. Calculate delta G0,000 quickly and very quickly for the reaction. Quickly, CH4 gas plus CO2 gas. H2 gas goes to CO gas plus 3 hydrogen gas. Happy to? Happy, Take a look here, At question, okay. At what temperature does K equal to 1? Does K big K, equal to 1? Because in which direction, quickly we answer this. In which direction does the equilibrium shift when the temperature of the equilibrated, the temperature of the equilibrated CH4H2O hydrogen, CH4H2O hydrogen, happy to gas mixture is increased. First question, or maybe second or third question, is increased question mark. B is the total pressure is decreased. The total pressure is decreased. You have to answer these questions, okay? So please, you keep complete writing, and then let us quickly take up the solution. I am helping you. Solution. See, delta G0 data is given to you, so you follow me with it. Wait a bit. This data actually I don't remember. Delta G0. Let me write CH4 solutions. Again, you write fresh CH4 gas plus H2O gas. Just quick solution, since this is an easy problem. By the way, this is very important to you to note that this is what type of reaction? The name, reforming of methane. Methane reforming to in the reducing gases. CO is a reducing gas, hydrogen is a reducing gas. You have reform. It can be reformed by H2O, natural gas. Reformed natural gas, it can be reformed by another one. You know which one? CO2 gas. Either H2O by CO or CO2. Or I tell you, CH4 can be directly used for reduction, but upon your HOIL middle X, you have read perhaps. So this reforming is used. You can note. Okay, very good. This is pertinent to delta G0. Say question is find delta G0 1000. You find delta G0 as some data is given. What data you require? Tell me. Nirjal, recall what is delta G0 formation in terms of formation? Oh, yes. Then plus no plus. Think no plus. Why no plus? No plus. Why not? Hydrogen, not compound. Hydrogen is not a compound. Only compound formation. Formation applies for compounds. Okay, it's okay though. It's okay though. So this data to apply, I'm writing you for you, and data given. So you write nicely. Data you actually cannot be slack, cannot be insincere. 87.65 T one data, first data. I'm giving you. These are data available. So I'm not writing twice. Okay, once only I'm writing, and I'm mentioning that these data are given. Okay, and last is water. Minus 246 000 plus 54.8 over soon. Easy problem to 82 joule, all joule. Happy to right? Data given in the problem. Data given in the problems. So I have written here data given in the problem. Oh, by the way, note it. This problem is from Gaskell. Gaskell, right? Gaskell second edition, which I have actually. I don't have the updated version. Second edition. Okay, Gaskell reference. Reference I will always give actually. See this quickly. If you do the simplify, you will get what answer? Simple 225410 minus 253.15 T joule. To this is over. To this is okay. Delta G0. Now question answer. First question. What is delta G0 1000? Easiest substitute 1000 and you answer. I am giving the answer is minus 27740 joule. You may try this problem. Answer. Okay, one answer. What is this? At what temperature does K equal to 1? K equal to 1 refers to what? Delta G0. What delta G0? At what delta G0 K becomes 1? Only 1. Easy. Delta G0 is right somewhere. Delta G0 is minus at tail end. Now tell me, at what delta G, at what?
Zero.
No, 1. Log 1 of G is 0.
No, del G0 equilibrium.
I mean, what do you mean? K is 1. Oh, thank you. K is referred to delta G0 is good. Is what? Delta G0 is, you right, correct. Delta G0, 100%. I'm sorry, I'm actually working backwards. Delta G0, 1, G is 0 refers to K is 1. Okay, very good. That means you know substitute here from 1. Call it 1, equation 1. from 1, substitute 0 is what? What is the temperature? Is what? Tell me. 225410 divided by 253.15. You everyone can solve this. Is what temperature? Tell me. 890 Kelvin. Answer. Again, answer. Okay, happy? Answer. Right. Answer. Two. Now third part means AB. Two parts are there. You follow temperature equilibrium has achieved. Now increase the temperature. What will happen? One temperature has equilibrium. Okay. As you change the temperature, equilibrium shifts. Equilibrium changes. Equilibrium constant changes. Hence equilibrium changes. So equilibrium condition is given by the temperature as well as the other things. Okay. Temperature equilibrium constant solely by temperature. Anyway, so if the temperature is increased, what is your comment? You follow this. Said if temperature is increased, reaction is forward direction. Which under what condition? Delta H0. Good. Delta H0. I said which reaction? Which relation it is? Van top. ddt ln k is delta H0 RT square or d ln. Okay, remember this. Recall. So write A. Actually, delta H0 is positive or negative here. Easy to tell me. First of all, tell me here. Delta H0 positive or negative? Why look at this? This is your A plus BT. What is this? H0 minus T delta S0. This is delta S0. This is delta H0. Okay. So delta, shall I write how many times I should write? Because this explanation I have given because at a given state, this is actually so delta H0 positive. Right? Positive. Or you write that one or negative. Oh, I don't see it. Oh, yes. 225.410. Write this as positive. Okay, positive. So what is the opinion? As you increase the temperature increases, what will happen? Tell me. It increases. What will happen? Positive. What will happen? Temperature increases. Equilibrium constant. What happens to equilibrium constant? Increases. Van top equation. Temperature. That means the reaction equilibrium constant increases means more of reaction. Equilibrium constant means more. It will attain equilibrium. Okay, after greater extent of reaction increases. So you actually, if you have a desired reaction, you want to have the equilibrium constant as high as possible, so that reaction is more and more. Okay, happy. So temperature increases. That is towards which side? Equilibrium constant increases means product side, towards CO plus, right? That toward CO plus hydrogen side. This is the answer. Which side? To the product side. Towards the product side. Good answer. But I am helping you. Be actually meticulous or say van top is the source. Lachiter principle. But Lachiter principle problem is what? That is qualitative statement. It will be favored. But what value? Here also qualitative question. So you can van top equation. What is that equation? Anyone? ddt ln k is delta H0 by RT square one form, another form, quick, or d ln k d of 1 by t. You can always two forms, d dt or d1 by t is minus delta H0 by any form you use. Actually, by the way, this is okay. This is over. This already you apply this. See here. This I explained in the class. I should not. Delta H0 positive means this is negative. This is negative means 1 by t decreases, ln k increases. Means t increases, k increases. Happy to? Okay. A. These answers. What is this? This is like A. Shall I write? A. I wrote A. Remember? A. B here. The last part. If pressure is decreased, what will this also I discussed. Give me an example of heterogeneous reaction. CO2 plus H2CO favorite. Okay, that you call it a carbon gasification reaction, Boulevard reaction, etc. There I use it. What is that? How do you say whether first of quick answer. Tell me which pressure is increased. Which direction it will move? Easy. Lachiter principle you may call it. Because fewer moles. No, pressure decreased. Greater moles. greater number of moles. If 4 here, gas mole. But here is really all gas. So no problem. 4 against 2. So to the product side answer is okay. Quality okay. But if you ask to find out, yes, at this increased pressure of what is the equilibrium state, then you have to calculate. So B is what? But how do systematically hold, right? Effect of pressure, right? Effect of pressure. Pressure decrease. Effect of pressure decrease. Quickly. Sorry, I unnecessarily wasting time. Effect of pressure decrease. I'm writing. There is K. Effect of pressure. Achha, K is what? Kx, recall, times P to the power delta N. You recall this. K is Kx P to the power, in terms of mole fraction. I'm not actually taking up this quickly. Kx delta N is what? Delta N is what? Tell me. 3 plus 1, 1 plus 3 minus 1 plus 1 is 2 is positive. The important is positive. So positive and pressure decreases. So this is positive. This is decreasing. This is positive. So the whole thing is what? Whole thing what? Delta N positive. Say P square. A P is decreasing. The whole thing is decreasing. This is decreasing. This side is decreasing. And what will happen to Kx? Kx. Why? If K is independent. Is K is independent? Yes, sir. When pressure is, the implication is what? Total pressure has decreased, means temperature has not changed anymore. When temperature is unchanged, no one can move equilibrium constant. Equilibrium constant is solely a function of temperature. I told you, like delta G0 is solely a function of temperature. So K, I write K unchanged since same temperature. Since same temperature unchanged. Since temperature unchanged. Since T unchanged. I think you get a clue there. So Kx increases. So what is the outcome? This is given to you. Delta N is given, P is given. What is the outcome? Kx increases. Kx increases means extent of the reaction increases. Again to the product side. This implication Kx increases. Right here. Can I remove this? Can I remove this? Remove. So just last line. Last line. Sorry, last line here. I am removing this one. Last line. Kx increasing implies the reaction moves to the towards to the product side. Moves to the product side. To the product side. Product means CO plus hydrogen side. That's it. Okay. One thing in passing. Note in here. Just okay. That's it. Answer. This is the answer, right? Answer means over. Achha, note in passing. I told you perhaps, but if you just tell me whether I told, but so important. Note in passing. Integration of Van top equation. Quickly, 1 minute. You should do yourself.